So today we want to do some calculations using electric potential and work. So remember, work is defined as the negative of the change in potential energy, and in the electrical case, the potential energy change is equal to the charge times the change in electric potential, V. Also from Physics 1, work is defined as force times distance, and in this case, for a charge in an electric field, the force is equal to Q times E. So in this problem, I have a proton which has a charge of plus E. It moves 15 centimeters towards the left in a rightward electric field of 1500 newtons per coulomb, and I'm asked to find the work, the change in potential energy, and the change in potential. So let's go through and figure out what we know from the problem. So every number, we're going to figure out what it is. So Q equals plus E. That one's easy. It's labeled for us. That's the charge. And the charge on a proton is equal and opposite to that on an electron. It's plus 1.6 times 10 to the minus 19 coulomb. It moves a distance of 15 centimeters. So that's my D in the equation, is 15 centimeters. I need to put that into meters, so divide by 100. Oops. So I get 0.15 meters. And the other number is that the electric field is 1500 newtons per coulomb. So I know Q, E, and D, and I'm asked to find the work. So if I look at the equations that I have up above, work is equal to QED, so that's easy. I've got all of those. It's just a matter of plug and chug. So work is Q times E times D. So it's 1.6 times 10 to the minus 19 is my Q, times E, 1500, times D, 0.15. And if I put that in, I get 3.6 times 10 to the minus 18, and the units for work is joules. Okay, so if you remember, we have to figure out work can be either positive or negative. Remember, it's positive work if it speeds up and negative work if it slows down. How do I know which it is in this case? Well, what I need to do is think about it. So I've got an electric field that's towards the right. If I put a positive charge in the electric field, it feels a force in the same direction as the electric field. And I'm moving it in the opposite direction. The field's to the right, I'm moving it to the left. So I'm making this thing go in the direction it doesn't want to go. And if I'm making it go in the direction it doesn't want to go, it's going to slow down. So if it slows down, that means that the work is negative. So I'm going to put a minus sign in front of the work. All right, next thing is what's the change in potential energy? Change in potential energy is just the negative of whatever the work is. So all I have to do is flip the sign from a negative to a positive. 3.6 times 10 to the minus 18. And again, the units is joules. All right, so I've got 2 of the 3. Now I need to find delta V. Well, remember delta PE is Q times delta V. So delta V is just delta PE over Q. And so I'm just going to put in my delta PE, which I already found, 3.6 times 10 to the minus 18, divided by my charge, 1.6 times 10 to the minus 19. Now remember, when you do this in your calculator, make sure you put brackets around the terms on the bottom so that you don't end up getting an error in your powers of 10. And when I do that, I get a potential difference of 22.5, and the units are volts. Okay, so that was relatively simple. The only thing we had to really think about was, is it going to be positive or negative? The next thing is to calculate the electric potential. So remember, the electric potential due to a point charge is K, 9 times 10 to the 9, times the charge, divided by the distance that you are away from the charge. And so that means that as the distance goes to infinity, the voltage goes to 0. And that's important for what we're going to do next. And also, the nice thing is that the voltage is a scalar, not a vector. And so if we've got a situation like the square shown at the bottom there, if I want to find what the potential is at that corner, labeled A, all I have to do is add up the numbers for the electric potentials from the other 3 charges, and then I've got my total potential. So VA is going to be V1 plus V2 plus V3. So whichever, let's say this is V1, that's V2, and that's V3. Then we're just going to add those numbers together and divide by the distance. So V1 is K times 3Q over the distance between 3Q and the point at which I'm measuring the potential, which is A. So that distance is L. If I look at the potential for charge 2, it's K times that charge, which is plus Q, over the distance to that charge. Distance to that charge is a diagonal, which is root 2L. And V3 is going to be K times charge 3, which is minus 2Q. And the distance between that blue charge and point A is L. So I can put in, if I'm given numbers for the charges and the length, put in the numbers, calculate a number for V1, V2, and V3. And note V1 and V2 are going to be positive, V3 is going to be negative. Add them all together, and I can get the total potential at point A. So let's do one where we've got some numbers. So here I've got 3 charges arranged in an equilateral triangle, and the sides of the equilateral triangle are 20 centimeters, and I want to find what's the electric potential due to those 3 charges at the center of that triangle. So V is going to be KQ over R. I know each of the Q's. What's the R? Well, the R for each charge is going to be the distance that that charge is away from the point at which I'm measuring the potential. So for Q1, it's going to be that distance. For Q2, it's going to be that distance. And for Q3, it's going to be that distance. Okay, so if I look at it by symmetry, R1, R2, and R3 are all the same. So I just have to do some trig to find out what's the length of that side R, and then I can calculate my potentials. So if I draw in a little blue triangle, you see there, that R that I'm trying to find, excuse me, is going to be the hypotenuse of the triangle. So the horizontal side of that triangle is half the side of the triangle, so it's going to be 10 centimeters. And I know that this angle in here has got to be 30 degrees because the angles of an equilateral triangle are 60, and I'm taking half of that angle. Okay, so I know that angle is 30 degrees. So if I look at it, the side that I know is adjacent. The 10 centimeters is adjacent. So 10 centimeters is equal to R cosine 30. So that means that R is equal to 10 divided by cosine of 30, or 11.55 centimeters. And so that's 0.1155 meters. And I'm going to leave it with all those significant figures actually as I do my calculation. So when I want to calculate the V total is going to be V1 plus V2 plus V3. Okay, so what's that going to be? K Q1 over R plus K Q2 over R plus K Q3 over R. I know my K is 9 times 10 to the 9. I know my Q's. So all I have to do is plug in the numbers. So let's go ahead and do that. So V is going to be equal to 9 times 10 to the 9 times Q1 is plus 4 times 10 to the minus 6 because it's micro coulombs divided by 0.1155. Q2, so I'm going to do 9 times 10 to the 9. Q2 is, again, 4 times 10 to the minus 6 coulombs. And the distance is the same, 0.1155. And finally, I've got K times Q3, and this time Q3 is negative. And so it's important when I'm doing the potential to put in the negative sign. And R is again 0.1155. They're all the same. So if I plug my numbers into there, I get a net potential of 3.1 times 10 to the 5 volts. Okay. If it hadn't been an equilateral triangle and all the numbers were different for the distances, all I would have had to do was put in the different numbers in the denominator for the distances. Okay, so last thing is to calculate how much work does it take to assemble a system of charges. So work is equal to the charge times the change in potential. So what we're going to do is we're going to imagine that all these charges start off out at the ends of the universe. So that means that R is going to be infinity, so V equals 0. And so we're going to calculate the change in voltage. The change in voltage is going to be the voltage of where they are in their final position minus their initial, which is going to be 0. So the change in voltage is just going to be the potential of where they are in the final position. Excuse me. So if I'm going to assemble the system of charges and I bring in the charges one after the other, the first charge that I bring in, that one's going to be free because there's going to be no other charges that are anywhere near it. So the work that it takes to bring in the first charge is going to be 0. Then when I bring in the second charge, that second charge has to fight against the potential from the charges that are already present. And so the work that I do moving that second charge is equal to the value of the moving charge times the potential due to the charge that's already there. And so let's say we bring in this plus Q first, then this next one that we bring in, if it's minus 2Q, is going to fight against the potential from the charge in the top left corner. Now if I bring in a third charge, that third charge, when I move it in, the work is going to be the value of the third charge, so in this case 3Q, times the potential that's already there. So it's going to be the potential from the first charge plus the potential from the second charge. So in this case, the first charge that I bring in, if that's the first Q, is going to have a work of 0. The next one is going to have a work of the charge that I move, the minus 2Q, times the potential due to charge 1 at the final position of charge 2. So charge 2 is going to be up in that top right corner. So it's going to be a distance L away from charge 1. When I move in the 3Q charge, the term out in front is the charge that I move, 3Q. And then I'm going to have the potential from charge 1 at position 3 plus the potential from charge 2 at position 3. So it's going to be K times the charge that's causing the potential and then divided by the distance between that charge and the one that I'm moving in. Let's do an example to see how it works. So we've got our same triangle again with the sides being 20 centimeters long. And now I want to calculate how much work is it going to cost for me to bring in the charges one at a time. All right, so if I calculate the work that a charge costs to bring them in, so first I'm going to bring in Q1. The other charges are all out at infinity. So remember, that means that the work to bring in the first charge is 0. So it doesn't matter which one I move in first, it's going to be free. So let me just write down the first one is free. All right, what next? Well, next I'm going to bring in charge 2. So charge 2, I'm going to bring it in, and the work that's done is equal to the charge that I'm moving, so that's going to be Q2, times the potential that's already there, and that's the potential from charge 1 at position 2. Okay, so Q2, 4 times 10 to the minus 6. And then the potential of 1 at 2 is going to be KQ1 over the distance between charge 1 and charge 2. So that's going to be K, 9 times 10 to the 9, times Q1, 4 times 10 to the minus 6, divided by the distance between charge 1 and charge 2 when charge 2 is in its final position. So that's going to be 20 centimeters or 0.20 meters. So in the denominator, I'm going to put 0.20. And if I do that calculation, I can get the work that it costs to bring in charge 2 is 0.72 joules. So that's a positive work. So that means that when I bring it in, I had to actually do some hard work to push it in. And why is that? Well, because I'm trying to push a positive charge next to another positive charge. You know they repel each other. So the closer I bring charge 2, the more work I have to do to push it in. Okay, so now let's bring in the third charge. So the third charge, the work done is the charge that I'm moving, Q3, times the potential that's already there. Now I've got 2 charges already there, so I need to worry about the potential between charge 1 and charge 3, and I need to worry about the potential between charge 2 and charge 3. So the potential between 1 and 3 is KQ1 over the distance between 1 and 3. Potential from charge 2 at charge 3 is going to be KQ2 times the distance between charge 2 and charge 3. So now if I go ahead and put in my numbers, Q3 is -4 times 10 to the minus 6 microcoulombs times V13 is KQ1, 9 times 10 to the 9 times 4 times 10 to the minus 6 divided by the distance. Excuse me. Now I want the distance between charge 1 and charge 3, which is going to be, again, just one side of the triangle, 0.2 meters. This configuration is very symmetrical, so it's made it very easy. Then they've got the potential between 2 and 3, so it's going to be K, 9 times 10 to the 9, times Q2, 4 times 10 to the minus 6. And again, the distance between 2 and 3, which is going to be the other side of the triangle, again, 0.2. And if I put my numbers in there, I get that work 3 is equal to -1.44 joules. What does it mean that it's negative? That means it's easy. That charge 3 wants to go to that position. I don't have to do any work, any hard work. I'm fighting to hold it back because it's attracted to Q1 and Q3. So now my total work is going to be work 1 plus work 2 plus work 3. And so that's going to be 0 for charge 1, 0.72 joules to bring in charge 2, and then minus 1.44 joules to bring in charge 3. So if I add those all together, I get a negative 0.72 joules. Okay, so that means that in general, that system of charges wants to attract together to be in that shape because it's negative. Okay, so let's see if you understand it. So the question that I want you to work on for your active learning question is, given this rectangle of charges, so charge 1, 2, 3, and 4 are given over on the side, I want you to calculate, first of all, in part A, what's the total electric potential V at the center of the rectangle. So that means you're going to have to calculate the distance of half the diagonal. So you're going to have to do similar trig to what I did. And remember, you're going to convert the centimeters to meters. Okay, what might be easiest for you to do is to calculate the distance of the complete diagonal and just divide it by 2. That's probably what I would do. And then for part B, you need to calculate how much work is required to assemble the system of charges. So if I start bringing in all these charges from infinity, how much work does it take to bring in charge 1, charge 2, charge 3, charge 4? Add them all up together to get you the total work to assemble the system of charges.